so this is day 10 of the 24-day physics question extravaganza, and today it's a weird one of those synoptic questions. That's a little bit of something and a little bit of something else. So this is actually materials and standing waves, which is quite interesting. So we've got a structure which is a horizontal wire used for transmitting radio signals. A copper wire is 12 meters long with a cross-sectional area of 1.6 times 10 to the minus 5. The tension in the copper wire is 5 times 10 to the 5, and the Young's modulus of copper. Show that the extension produced in a 12-meter length wire when tension is less than 4 millimeters. So they're giving you lots of information here. So we're going to be using predominantly a lot of things with Young's modulus. So of course, Young's modulus is stress over strain. Okay, and the extension, of course, is to do with strain. So if I can find the strain, I can find out the extension. So stress is force over the area. So that's going to be the tension is a force. So that's 5 times 10 to the 2. So it's over the area, over the cross-sectional area, which is 1.6 times 10 to the minus 5. So my stress is 5 times 10 to the 2. Divided by 1.6 times 10 to the minus 5, which is quite a big number of 31.25 times 10 to the 6 there. Okay, so my strain is going to be my stress divided by my Young's modulus. So strain equals my stress, which is 31.25 times 10 to the 6, divided by my Young's modulus, which is 1.2 times 10 to the 11. Here. So my strain is going to be 0. Whoops, no, not 0, sorry. It's going to be 2.6 times 10 to the minus 4. So strain here is change in length over my length, okay? My original length, so that's 12 meters. So 12 times by 2.6 times 10 to the minus 4 is 3.125 times 10 to the minus 3 meters, which is about 3.13 millimeters, okay? So so if you get Young's modulus, it's kind of like when you get density, and we do actually get a density question like here. What I tend to do is some students will tend to write this really big equation, and they'll try to end up with this. They'll go Young's modulus equals F over A over change in length over L. And that's fine. You can work with that if you want. I tend to like working in spates. I tend to go, okay, what is the stress? What is the strain? And that's fine too. And it's a methodical approach, and you can take either one that you wish. So in a show that question, you are just trying to prove that this is the case. Okay. So this is worth 2 marks. If I just grab the mark scheme here. Okay, we've got the information we've got here is use substitution of data actually into the formulae, and then the answer 3.1 times 10 to the minus 3 there. So 1 mark for the answer and 1 mark for my method. Okay, so the cables that support each other at the mast are at 65 degrees to the horizontal. Calculate the tension in each of the supporting cables so there is no horizontal force in either of the masts. Okay, so what's actually happening here is there is a tension. There is something pulling this with 500 times 10 to the 2. And so you got here and you got here. And it's asking you to find the tension in the cables. We've got tension here. So this is, I know that the force pulling it this way is 5 times 10 to the 2. Okay, so I know that T cos 65 equals 500, because doing shapes here, 65 there. Okay, so my tension is going to be 500 divided by cos 65, and I get 1183. Here, it's only 1 mark question. You only literally get it for the answer. So I've got it for 1,200, Okay, here. There's not any point that's saying any significant figures. You would actually get a mark for the actual answer here. Okay. So this is what's happening here. I know that it's the copper wire is being pulled this way with 500 newtons. I'm trying to find the tension in the cable that's actually doing that. Okay. Okay. So when the wind blows, a stationary wave performs. So this is becoming now synoptic because I'm going from Young's modulus to standing waves. So when the wind blows, a stationary wave is formed. Explain. So remember, explain, you must have because in the answer. Explain how stationary waves are produced and only why specific frequencies can form a stationary wave in the wire. Okay, so it's 4 marks. You can pause the video here and see if you can get this answer. And you can play me again and I'll go through that. So let's go through this. So there's 4 marks. So explain how stationary waves are produced. So you're going to be saying 4 marks. You're going to be saying 4 things. So clearly you're going to be saying quite a bit about why they're produced and why only specific frequencies can form. So that last thing is probably only worth 1 mark. So how stationary waves are produced. Okay, so stationary thing is so when the wind blows. Okay, stationary. So explain stationary waves because when the wind blows, a wave forms on the wire. The wave is reflected, this is point, back at the ends. The forward and reflected waves superpose on each other, causing a standing wave. So what I'm explaining here is that I'm saying that goes, when a wind blows, a wave forms on the wire. The wave is reflected back at the ends, and it's this idea of that forward and reflecting waves superposing on each other, causing a standing wave. If I grab the mark scheme for that, if you look here, the wind produces a wave along the wire. The wave is reflected, and then those waves superpose on each other. So it's superpose, not superimpose. And the last thing is like mentioning about why only specific frequencies can actually do this is that there we go. There needs to be a node at the ends for a standing wave. So this is important that for a standing wave, there must be a node at the 2 ends, okay? As you can see here, only certain frequencies since fixed ends have to be nodes, okay? So this kind of thing, explain. Why is that there is a stationary? Because when the wind blows, a wave forms on the wire. This means there is a wave reflected back at the ends. This forward and reflected wave superpose on each other, which causes a standard wave. And you can only get certain they only get certain frequencies happen because there has to be a node at the end for a standing wave to be produced. Okay, so that's 4 marks. 4 bullet points, 4 marks. Okay, so calculate the mass of a 1 meter length. I'm given the density. So you can pause the video now and do exactly what you think you're going to need to do for this, and then come back and check. Okay, so density. You write the density formula out, mass over volume. Okay, so for a wire here, so it's asking calculate the mass. So that's going to be volume times volume is your mass. So your density is 8900. Now your volume of a wire is the length times by the area. So in this case, your length is 1 times by 1 times by your area, and you were given that information right at the beginning of the question. So that's going to be 1.6 times 10 to the minus 5. So putting it onto calculator, so 8900 times by 1 times by 1.6 times 10 to the minus 5, and we get an answer, 8 900 times 1.6 times 10 to the minus 5, we get an answer of 0.1424 kilograms there. Okay. Okay, so this one here, calculate the frequency of a harmonic is formed. So calculate the frequency of a wave when the third harmonic is formed. So in your data sheet, you are given the frequency for the first harmonic, which is frequency equals 1 over 2L, the square root of T over mu. Okay, and literally by just having that formula, you can get quite a bit of information there. So this is, oops, here. So you calculate when the aerial wire. Okay, so this mu, this always catches student out. This is the mass per length. Okay, and I've worked out the mass in the question before. So that's 0.142 kilograms per meter. Okay, so I can put that mass per length, so 0.1424 per meter. So I can actually put that in there. Okay, so I can work out the frequency of the first harmonic with all the information I've got. So I've got my 1 over my length is, of course, 12 meters. Okay, times the square root of the tension, which is going to be 500 newtons, divided by 0.142. So I've got 500 divided by that. I've got the square root of that, and I've got times by 1 divided by 24. I've got 2.47 hertz. And that is for the first harmonic. Okay. For the third harmonic, I'm going to want to times that by 3 and get an answer of 7.41. And this is the third harmonic. So we can look at the mark scheme for this one. Here we go. So the first harmonic is to find the fundamental, so 2.47. So you've got all the information there. It's the mu that kind of slips people up, okay? And the third harmonic, of course, is 3 times the first harmonic. So sketch, I love these ones. Sketch on the thing, the third harmonic. So basically you should have, I normally just draw like this, woo, and you should have 3 bumps like that. There you go, with nodes at each end. So there we go. That's just the third harmonic there. So high winds produce very large amplitudes in the wire. So they have very large amplitudes in the wire. Explain why the wire may sag when the wind stops. So this is going back to material science. Okay, so this is going back to where high winds equal high forces. Okay, so high winds equal high forces. So what could actually happen is when you put a really high force on copper, you may stretch it beyond its plastic limit. So it's asking why it's going to sag, why it's going to be longer than it was. Okay, so high winds equal high forces. The copper will stretch and could stretch past its elastic limit and permanently change shape. Okay, so explain why the wire may sag. The wire may sag because there are high winds, which means high forces. This means the copper will stretch and could stretch past its elastic limit and therefore permanently change shape. That question there is worth 2 marks. So mention the fact that it could be stretched beyond its limit, which means it won't return to its normal shape. So it's one of those things that in that kind of question, think about what the question's about. So in this case, it was a material science and standing waves question, and go, well, they're asking why the wire may be a bit different afterwards. That's a material science thing. Why might it be sagging? Because it's got longer. Okay. So there we go. That is a synoptic question for Unit 10 on materials and standing waves.